Last time we introduced the Hartree-Fock approach, and by second-order perturbation, we are able to write down this so-called direct and exchange processes, which will lead to the corrections to the zeroth order non-interacting isomorph results. So let me just write down these two possibilities. First, the direct, where we have this Q equals 0. And this is going to give you, say, V0, where Q is actually 0. And we know that this goes to infinity. And this infinity is precisely the infinity that we tried to eliminate last time. Remember, we sum up all these infinities of a Coulomb interaction. Because of charge neutrality property of solids, and if you sum up all these infinitely large Coulomb interactions between electrons and electron, also between electron and ions, which is attractive, and also between ion and ion, which is repulsive, and it is equivalent to actually sum up all the charges. And when you sum up all this positive negative charge in your solids, and you get 0. So we don't worry about this V0 here, because this is precisely this potential energy between two electrons, which is repulsive energy. And then when we sum up all the other infinities, we'll get 0. So we don't worry about this. So we should focus on this exchange processes, where the initial state K becomes K prime, and K prime becomes K. And you get this K prime, and K prime to K VQ. So now this Q is non-zero, and K prime is what? K minus Q, or Q is actually K minus K prime. It's called momentum transfer. So these two electrons exchange their momentum, and there's a momentum transfer between these two electrons, so that their momentum, initial momentums, get switched over. And we could use these two diagrams to illustrate these two processes. The exchange processes happens between any two electrons near the Fermi surface, but because of this Coulomb interactions, they actually exchange their momentum like this after scattering. But this direct processes is a process that this two momentum does not exchange any momentum Q, but the initial and final states is actually the same. So then we forget about this direct energy, and we simply focus on this exchange energy. So the Hartree-Fock energy is given by this kinetic energy of the free electrons, and plus this exchange energy, okay, which is this. So now we need to study this, as we emphasized last time, that the initial states and the final states should be the same in order to actually have this non-zero matrix element, right? So this phi is the unperturbed eigenstates of free electron gas. And all this K and K prime here represents precisely the unperturbed eigenstates of free electrons. It's just that they are interacting by Coulomb. Okay? So after considering this exchange processes, we get this. So what next? Well, the next step is trying to simplify these four fermion operators by using these anti-commutation rules, and to transform this four fermion into the function of occupation number operator. So let's do it. So this four operator is reduced to this one. Suppose I try to interchange these two. by using this anti-commutation rule. Okay? So first I interchange the middle two operators. I get this by using this anti-commutation rules. And the last one, I simply just copy this. Okay, so now what's next? Well, the next is to actually expand these two terms, right? So this is C delta K prime, C K delta K prime minus C delta K prime, C K prime, C delta K, and C K. Okay, so what's this? Well, this is nothing but C delta K, C K, because if K is not the same as K prime and you get 0, so this term survives only when K equals K prime. So therefore, you get this n of K occupation number operator times delta K prime. Of course, this delta K prime should survive because we haven't summed over all these indices. So we should sum over K and K prime. Okay, so what about the second term? Well, second term is really simple because remember this is just n K prime carrying a hat, which is a number operator, of electron, where the electron state is actually in the K prime state. What about this, the other two? Well, this is simple, right? So now this four operator object becomes a function of this occupation number operator, which is exactly what we need. We need to transform all these messy operators into something that we know, because the number operator, when you take the absolute value, is nothing but the Fermi-Dirac for fermion system, and it is the Bose-Einstein distribution function for bosons. Okay, and we know this Fermi-Dirac at finite temperature. Therefore, we know this kind of a second-order perturbation at any finite temperature. And the problem is quote-unquote solved. Unfortunately, Hartree-Fock doesn't give us a reasonable result, but this is doable. It can be done. Okay, at least we can do some calculation. Okay, good. So let's do it. So then this Hartree-Fock energy becomes this K minus K prime magnitude square and K prime and K. Of course, there is another divergence here. So remember, we have this first term, which is a single occupation number, and K varying hat multiplied by delta K prime. But if you combine this Coulomb energy here with the occupation number, you see immediately that this is nothing but V0. Okay, so V of K minus K prime times delta K prime times n of K is nothing but V of Q equals 0. All right? So this is another infinity that we don't care about because, as I mentioned, whatever this infinity you get, after all, because of the charge neutrality condition, when you sum over all this divergence of V Q equals 0, you should get 0 because of a charge neutrality. So we simply just don't care about this because of charge neutrality. So the charge neutrality condition is a physical limit, but all this divergent term can actually come up in some kind of intermediate steps. But if you sum up all these divergent terms, you should get non-divergent results, which is physical, and so that we don't care too much about this at this point. So we only care about this second term here, which is this. And remember, there's a minus sign here in between these two terms, so that there is a minus sign here if you simply just copy this here. All right, so this is the exchange energy that we are talking about. This is exchange energy. And let's just further simplify this. So it is epsilon 0 minus sum over k and k prime, which are occupied, and 2 pi e squared over k minus k prime magnitude squared. So if you evaluate this matrix element nk and k prime sandwiched by this non-perturbed eigenstates, and you will get simply just Fermi-Dirac n of k times n of k prime. So this is Fermi-Dirac. This is precisely what we look for. Therefore, this is simply just telling us that for n of k and n of k prime, we need to really multiply this of 2 Fermi-Dirac function, and to really find this intersection where both n of k and n of k prime are non-zero. At 0 temperature, this is nothing but this kind of an intersection between these 2 Fermi spheres. Right, this is n of k and this is n of k prime, and both k and k prime are momentum for this left and right Fermi sphere, and the occupied states refers to the states inside this, say, left Fermi sphere, and also we need to consider the occupied states of the other Fermi sphere. And so this product between these 2 Fermi functions is telling us that we need to actually count this volume of this intersection region. Okay, so this is what we need to do. So let me just use this blue to represent that this n of k and n of k prime is non-zero. Okay, so on either side of this yellow or red only shaded region, either of this Fermi function vanishes. So in this case, it is n of k being 0, but n of k prime is finite, which is 1. And here it is the opposite. N of k is 1, but n of k prime is actually 0. So at 0 temperature, limit, we need only to care about this intersection between these 2 Fermi spheres, because on the other side, either side of this intersection region, either one of this Fermi function vanishes in 0 temperature limit, so that the product of these 2 Fermi function is 0. So in 0 temperature limit, we only need to pay attention to this region. Of course, in finite temperature, so this product does not vanish just inside this intersection region, but there's some larger region that this product becomes finite, but don't worry about this at this point. And that's why I mentioned, define that both k and k prime should be occupied. And this is precisely this blue region here, that k and k prime are both occupied. So then the remaining job is to actually sum over this Coulomb energy with both k and k prime being occupied. And this can be done and has been done in Kittel's textbook. And so you could check our textbook for this algebra. And I'm quoting this final results, but let me just comment on this minus sign a little bit. So the minus sign here, this minus sign here, there's a reason for that. It is because the Pauli exclusion principle and also the antisymmetric wave function for fermions or for electrons. So remember, these exchange processes occurred when we exchanged these 2 electron states after the Coulomb interaction, right? So we really exchange their wave function. Okay, so when we do this exchange thing, there should be a minus sign emerges by doing so. And that's precisely this minus sign comes from. Okay, so we exchange these two electron states, and therefore there's minus sign appears. Okay, right. So, and you can see that in another way. Suppose I exchange these two particles between R1 and R2, and total wave functions actually flip the sign. Remember that the quantum mechanics tells us that this total wave function for two fermions flip the sign when you exchange these two fermion wave functions. And this flipping the sign when exchanges these two fermion wave functions will lead to the negative energy corrections. And that is precisely the Pauli principle is telling us. So the total wave functions actually vanish right when R1 is equal to R2 to actually avoid that two wave functions bump each other. And such kind of avoiding two fermion wave functions to collide in terms of energy consideration, it leads to the reduce of the total energy, and therefore you got minus sign there. Okay, which means that these two electron wave functions actually get more stable if they are away from each other. So if they're too close to each other, and the system becomes unstable. Okay, so the minus sign in the energy correction that we just calculate has the origin of the Pauli exclusion principle, that these two fermion wave functions do not overlap at zero. Okay, and which means that their energies must be lower if they are away from each other, and the energy is actually positive or higher or unstable if they are too close to each other. Okay, so the reason why we get the minus sign is because the energy is actually lower, and by keeping them away from each other. Okay, so this is a direct consequence of the Pauli principle. And so far we have not included the spin yet, but we will do that in just a moment. Okay, so let's include the spins in the exchange processes. So remember, when we pair them up, this four fermion operators into two pairs of two fermion operators, one dagger, one non-dagger, we forgot about the spins, but now we should include them right here. Suppose the first operator, C dagger K minus Q, carrying spin S, and K prime, S prime, and K prime, S prime, and K S. So when we exchange these two, and we get the condition that S and S prime should be the same. Remember that, right? So when we really pair them up, so not only does this momentum should actually match, the spins also need to be matched, right? So there's end of K or K prime or whatever, delta S, S prime. So in other words, if so let me just write down this C dagger K prime C K C K prime C K. So remember, when we interchange this, we got dagger K prime C K prime C dagger K C K. But when we derive this up to here, we should remember that the spins of these two operators should be the same. Otherwise, we don't get the Fermi function. Okay, so the Fermi function is actually defined as what? S C K S. Okay, so this expectation value for this number operator, C dagger C, should carry exactly the same spin indices or quantum number. So if we consider this up spin C dagger with a down spin C k, you get 0. Okay? So it is because the spins are not the same. Okay? By definition, the occupation number is defined by destruction operator and creation operator, where both operators carry the same quantum number, including the momentum and the spin. So there should be exactly the same state. So the spin should be the same.
So the Coulomb action will not let the spin flip, right?
No. The answer is yes and no. And the reason why we have only the same spin species that are interacting is because of the Hartree-Fock. So don't blame the Coulomb. The Coulomb interaction is innocent. Okay? The guilty one is the Hartree-Fock, so which would be discussed in just a moment. Okay? So
Another question.
right.
In general, we talk about scattering. We see the final state will far from the scatter. So even the scatter, after scattering, and then the length is over the spin coherent length, maybe also spin flip, right?
The point is that within the second order perturbation of the Hartree-Fock approach, there is no way that spin up electron interact with spin down electron, because of precisely this point. If you pair up, there's no way that S is not the same as S prime. If this is the case, you get 0, nothing. So there's no way that the spin up electrons can interact with spin down within this framework. It doesn't necessarily mean that spin up electrons will never interact. In fact, the truth is the opposite. Of course, the spin up electrons can interact with spin down electrons, but not within the Hartree-Fock. So this proves that the Hartree-Fock is wrong, precisely because there's no way that spin up electrons interact with spin down electrons, which is wrong. But we need to learn what's wrong with Hartree-Fock first, before we correct this wrong approach. Okay? So you raise an excellent question. So everyone understands this question. Okay? So within this second order perturbation, S must be the same as S prime, otherwise you get nothing. But this result is totally wrong, because we know that spin up and spin down electrons certainly can interact by Coulomb. Why not? Okay? So this proves that Hartree-Fock has problems, but we need to know what the problem is before we try to correct them. All right? So in other words, in this Hartree-Fock approach, only the same species can interact within each other. So let me just summarize this Hartree-Fock, including the spins, K and K prime. We need both up, up, or down, down, and K minus K prime. Great. So there are only two possible spin terms that could add to this summation. One is K and K prime are both up. Another is when K and K prime are both down. So then you get the factor of 2 here. All right, so here comes the homework. So we know this epsilon 0, the zeroth order, which is 2.21 divided by Rs squared, Rydberg constant per particle. What about this Hartree-Fock exchange energy, which is 0.916 divided by Rs? And derive it. So to derive this, it is not difficult, because this is already done in your details. So let me just write down part of this calculation. So at the end of the day, you will calculate this stuff, the intersection between two Fermi spheres, and each of them is centered at a different momentum, K and K prime, respectively, and that's it, right? Okay, at 0 temperature, and either Oscar Mermion or Kittel. So let me tell you where you can find this. Page 91. Okay, so you can easily find this integral. It's nothing but calculating this overlap volume between these two Fermi spheres and integrated this function 1 over k minus k prime square. So let's continue. Speaking of spins, so you could evaluate these predictions from Hartree-Fock for various kinds of metals, and in particular, the Hartree-Fock theory favors the ferromagnetic states, ground state, meaning all the spins point to the same direction, and this is inside the metal. It's called a ferromagnetic metal. And we will come to that in just a moment, but let me just tell you that the Hartree-Fock theory, because of these interactions are between same spin species, then this Hartree-Fock theory favors ferromagnetic metals. So many metals that are not ferromagnetic, but they become ferromagnetic within the Hartree-Fock. So the Hartree-Fock incorrectly, so this is wrong, incorrectly predict many metals to be ferromagnetic. So I mean incorrectly. So these metals are non-magnetic or other magnetic, but within the Hartree-Fock, they are always ferromagnetic, which is certainly wrong. Okay, so and this is the reason why this Hartree-Fock is wrong, because within such second-order perturbations, only same spin species can interact by Coulomb. Okay, so we cannot do anything about this, because that's the Hartree-Fock approach from the beginning. So we should abandon this Hartree-Fock later. But let's just, because this is a classic example of Coulomb interacting many-body system, so we need to understand what's wrong with the Hartree-Fock. So let's just compare the experiments, Hartree-Fock to the experiments. So there are many things, almost everything that could be measured in the laboratory, and the Hartree-Fock theory fails to actually account for almost all the observables that we know. So let's check the first property, so-called the electron-hole pair excitation or elementary excitations. So the energy cost for such an electron-hole pair excitation. So remember, in the very beginning, we mentioned this two thin shells inside and outside of the Fermi sphere that allows for such electron-hole pair excitations. Such electron-hole pairs are called quasi-particles. Remember that. And so now we can really calculate this energy cost to create such a quasi-particle electron-hole pairs within the Hartree-Fock. So suppose that we have such a excited state electron state called P prime, and the original so-called Hall states within the Fermi sphere carrying momentum P, and we should create one electron with the energy being P or P prime, and this cost energy WP, energy cost. And how do you calculate this? Well, remember, the total Hartree-Fock energy consists of what's the free electron kinetic energy plus the negative value of exchange energy. Remember that, right? So let me just tell you this. Or Hartree-Fock epsilon 0, which is in terms of the occupation number operator, this is nothing but this minus k prime and 2 pi e square spin and nk prime. Right? So that's what we got. So this is the total energy within the Hartree-Fock, and to create an electron in excited state with the energy P or momentum P, what we need to do is actually to take the differentiation of this total energy with respect to this number operator or occupation number, which is simply to say that how much energy does it cost per particle to have such an electron state with a momentum p. Okay, so this energy is actually given by partial epsilon Hartree-Fock, partial the average occupation number of electron at the state p. You get that? Okay, we have the total energy, but this energy is a function of occupation. Okay, when you sum up all this possible k and k prime, you get total energy. But what we need to know is how much energy is required to have such an excited state electron carrying momentum p per electron. Therefore, we need to actually divide this energy by the occupation, by how many electrons are there, right? Okay, to get the energy cost per particle. So this is just half of the story. Another story is that we need to have a hole, to place a hole here, right? So this amount of energy is allowed us to put the electron in there, but we need to put a hole below the Fermi sphere. And then we need to actually subtract this energy between putting the electron and putting the hole, and to get the total energy, or net energy, to create the particle hole excitation. So I use up all the space of this blackboard, but perhaps we should stop here for today, and we'll continue to evaluate the predictions from the Hartree-Fock approach, in relation to the experimental observations. So in short, this energy could be measured in the lab. So we could measure precisely the quasi-particle energy, okay? Energy cost per particle hole pair. But this energy within the Hartree-Fock really diverges, okay? So let me just show you this final result. So this is actually infinity within Hartree-Fock. So this is the final answer. Very disappointing answer. But even though the Hartree-Fock is completely wrong or not correct, not accurate, but this is a very good starting point to actually address this many body phenomena in metals. So enjoy this failure of the Hartree-Fock, and we should learn from the failure. So that's the success or the history of a science, that we make the breakthrough based on millions of failures. So failures are really a good lessons in science, especially in physics. So without failure, we cannot make any progress. So that's the statement we need to remember. That. So that's why this failed theory is really excellent lessons that we can learn. And in fact, in the history of a solid-state physics, we learn from this mistake, and not mistake, it's a failure. It's just try and error. Once we find that this is wrong, then we should find what's correct. And then we should use a different approach, orthogonal to this approach, and then we succeed. And that's the idea of the density fluctuations in the solids. So we abandon this Hartree-Fock naive second-law perturbation. We should focus on the electron density operator itself, rather than just the energy of this individual free electron state. Okay? So that's the real history of a solid state. Okay? So we really learn from the failures and mistake. Failure is part of our life and his study or exam, or you'll experience millions of not successful experience in your life. So we should treasure this failure. So good. So I'll see you next Monday.